Hello, hello. Welcome to our second Saturday Engineering for Everyone, spring of 2016. It's great to see such a crowd here. I heard our talk last time was spectacular. I unfortunately had to be out of town, and I'm glad to see all of you back this time. My name is Scott Carney. I'm one of the co-organizers. Before we get going, I'd just like to recognize and thank one of our graduate student volunteers, Arti over here. Arti has been oh, come on, stand up for a second, Arti. Hello. So give her a hand. Arti's been helping with the logistics of organizing everything, which actually is quite significant, and so I really appreciate the help. Thank you, Arti. I have my cutie for the day up here, my boy Leaf. Leaf wanted to come up and help introduce everyone. Before we get going, I'd like to make a quick announcement. There are flyers outside on the table for Pollen Power, a summer day camp for middle school girls. It'll be up at the Institute for Genomic Biology, or IGB, and I'd encourage you, if you have a girl in your life who would be interested in doing a summer camp at IGB, pick one up on your way up. So, on to the business at hand. Today we have Professor John Thaler. John is an old friend. In fact, I knew John way back in the day when I was a student here, and John was still doing high energy physics and discovering the laws of the universe at the microscopic scale. John did his undergraduate and PhD work at Columbia University, went on to a postdoc at Princeton, and has ever since been a professor of physics here in our own Department of Physics at the University of Illinois. About 15, 16 years ago, he made the transition from the physics of the very, 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 very small to the physics of the very, very, very big. And so John has been doing cosmology and astrophysics for the last decade and a half. Those two things actually go together very, very well, as you'll hear today. And without further ado, John Thaler.
Just like lecturing in Loomis. Okay. I think it's so. I'm getting a lot of feedback here. Maybe if I lower it down. Can you still hear me? Good. All right. So I'm going to, well, as the title says, I'm going to talk about the history of astronomical telescopes, starting with Galileo and going to the near future. This is a picture from the first slide, and this is a picture from the last slide. One of these is a project I work on. I would just want to point out, I'm hoping that this talk isn't too long. That's why the word brief appears twice in the introduction, because I really had to do a lot of work to try to avoid putting all of the neat things that I think belong in. Suddenly change. There we go. All right. So anyhow, we'll see how it goes. By the way, outside I have two demos of the optics of Galileo's telescope. Obviously not quite the same fancy leather covering, but the optics are identical. And so you can, after the talk, you can go out there and try to see something through one of these telescopes. It will make you appreciate how difficult a job it was for Galileo actually to do what he did. The other thing one of the main themes of the talk will be that each of these instruments at the time of its construction was state-of-the-art. So in 1609, this was the state-of-the-art for optics. And this is now, at least in one direction, the state-of-the-art in telescope making. So we'll see. One of the themes is how the progression of that optical technology has enabled the progress of physics and our knowledge of the universe. So I'm not going to go through the outline in great detail. The important point is, so I'll talk about the beginnings. I'll do a very brief discussion of how telescopes work, the kinds of science that this dot will actually go all the way through the talk. as we have each of these different developments, clocks, photography, computers, space, each of these technological developments enabled more reach in our science, and so I will try to make the connection between the technology and the science that's enabled by each of them. And then I'll spend a little bit of time talking about the near future. From my point of view, the two main topics for the near future are understanding dark energy and dark matter. That's the project I work on. And the other big one is the study of exoplanets and maybe the discovery of life on other planets. So just a warning, there has been some big news in astronomy in the last month or so. I'm not going to talk about it. Anyhow, I'm not an expert on gravitational waves. If people have questions at the end, I can answer some of the simpler questions. But I'm sure there will be a talk on this topic probably in the fall. Maybe over in physics, maybe here in ECE. I don't know, somewhere on campus, I'm sure there's going to be a talk about this. I will also only talk about optical telescopes, no radio, no X-ray, no gamma ray, all of this stuff. Very interesting, but this is only a 1-hour talk, not a whole course. So anyhow, so in the beginning, it's interesting, where did the telescope technology come from? It came from the need for people to read the newspaper. So in fact, there's a connection between the invention of the printing press and mass publications and the need for large numbers of people to wear eyeglasses. And that requires spectacles require one lens in front of each eye. The invention of the two-lens combination was sometime in the early 17th century. This was all centered, the Dutch were the leaders of this technology at the time. It was originally, interestingly enough, regarded as a military secret, because you can spy on your enemy. But Galileo heard about it and made his own. There's another branch here. Compound microscopes were invented about the same time, and the whole development of microscope technology enabled, in a similar way as what I'm going to describe, advances in biology. But again, that's not my topic. So at the time, it was, from our point of view, the quality of telescopes was limited by the technology of the time, the ability to make surfaces with a known curvature so that you can control the focal length of the lens, and by actually the optical quality of the glass, which wasn't very good. So that was the beginnings. So just very quickly, how do lenses work? So what a lens, I'm not going to go through the thing. Basically, a lens, if the light comes into a lens, it focuses it to a point, and you have a focal length. If you hold the lens right in front of your eye and look at a piece of paper with some words on it, you will see an image. This is what you see. This is what's really there. This is what you see. You see a bigger version, and the reason I'm talking about this is the important thing is when you talk about magnification, what is it that we mean? What we mean is the angular size of the image. So let's look at two words here. So this maybe is the original one. This is the magnified one. This is a magnification of 2, because if you look at this side of the word, you have to turn your head by a certain angle to get to the other side of the word, and that's about a factor of 2 here. Now, the reason I'm stressing angles is that telescopes are great at measuring angles. There's a star up there. It's easy to measure the direction you have to point your telescope to see the star. It's not so easy to tell how far away the star is. That's the single most difficult measurement to make in astronomy, is distance. And so this is a problem that has plagued us forever. And so I'll spend some time talking about how you measure distance, because that's an important thing in cosmology. How big is the universe? Just to stress this point, so you suppose you're looking at these two objects, one of them looks bigger than the other. The question is, Is the orange object really smaller than the red one, or is it merely farther away? And without some knowledge of some independent knowledge of that distance, derived some other information, you can't tell. Okay? So size is one way of estimating distance. Brightness is another. So here's a photograph of two objects in the sky. The question is, which one, these are two planets, which one's farther away? I'm sure you can probably figure it out. But if you didn't know, if you didn't have some other information, the obvious thing would be, well, this is a closer object, but it isn't. This is Jupiter, and that's Mars. And you may have figured that out from the two little dots next to Jupiter. But anyhow, I just want to point out that brightness can also be a very misleading measure of distance, unless you have some other way of knowing what the intrinsic brightness of the object is. Then you can use it to estimate the distance. Okay, so anyhow, that's one of the continuing issues in astronomy, is how to measure distances. So how does a telescope itself work? Telescopes have at least two lenses or two optical elements, usually. This is the optics of Galileo's first telescope, and the ones, as I say, the ones out there that you can look at later, this is what they are. They're in cardboard tubes, but the optics is identical to Galileo's optics, except that our lenses are much better quality than his. Oh well. That wouldn't have helped. If you look through the telescope after the talk, you'll see it's very difficult to see to see things. So I'll show you what he did. So anyhow, so you're looking at objects really far away. If you set up the optics right, you get an image that's also very far away, but bigger. Okay, so that makes it easier to see details of the image. And the ratio of the two sizes depends on the ratio of the focal lengths of the two lenses. It's just the ratio. Anyhow, I'm not going to talk about that. Galileo actually was not a professional optician. He used telescope designs that other people provided to him. So any advances in telescope design technology. Kepler, on the other hand, whose name you may know, actually did do some of the big improvements in telescope design. But I'm not going to talk about that too much. So here, these I think are some of his original telescopes. The first one he built had a magnification of 3. The ones that he used and the ones that are outside have a magnification of about 10. And okay. And as I say, one of the lessons to take away when you look through them is how difficult this science was at the time, because he was really using cutting-edge state-of-the-art technology, which basically was handmade, and I'm sure it was not so easy to do. So, all right, so what did he do? For one of the things he looked at was the moon. One of the features of his telescopes was, well, the important thing that let him do new science was, because of that magnification, he was able to do he could see details about 30 times smaller on an object like the moon than Tycho Brahe, who was the best naked eye astronomer of the previous century. And so that let him make a map of the moon. This is his drawing of the moon. To give you an illustration of how hard it was, this is how much of the moon he could see with his telescope with any one pointing. So in order to map out the moon, he had to, look a whole bunch of times. And one of the things he discovered, so that's one advantage, is the magnification. Okay, the other advantage is that the telescope has a lens that's about this big, about couple inches, 5 centimeters. That means it's collecting more light than your eye, which is only a few millimeters, and therefore he could see fainter objects than the naked eye. Okay, so that was why he was able to see Jupiter's moons, because they're not very bright. That photograph I have is actually time exposure, which is why you can see Jupiter's moons in that time exposure. So what are some of the undesirable features? Well, I mentioned already, it has a very small field of view, which makes it difficult to map out big objects. That's not good if you want to do a big survey, and you'll see the project I'm working on wants to survey the entire sky. You're never going to do that with a telescope with this kind of field of view. And the other thing is it's hard to find things if you don't know where to look. When you go out there and look across the quad at the building across the quad, try to point at like one of the street lamps. It's not so easy to find even a street lamp with this telescope, because you move it a little bit and it's out of your field of view. So I'm amazed how difficult it was. I hadn't appreciated it until I had my hands on this telescope, was actually trying to use it. The other thing he looked at, so what did he learn here? He learned, well, actually on the next slide I have some of the scientific things that he discovered. You can see one, here's an important feature, that this tells you where the sun is, because there's a big crater on the moon, and you can see that it's being illuminated from the right here and from the left there. And yeah, we'll talk about that kind of stuff. The other thing he saw was Jupiter. Looking at Jupiter, he discovered stars, well, what he thought were stars, but then realized after looking at them day after day, week after week, they're moving around, and he realized that they are orbiting around Jupiter. Okay, the 4 brightest moons of Jupiter, called the Keplerian moons, those are the ones he discovered. So here's the science enabled by this. So he saw the moons of Jupiter. This was important because it showed, contrary to the older version, remember that here's the old cosmology, the Ptolemaic or Aristotelian cosmology. The Earth is in the middle of the universe, and everything is moving around it. Okay? What the moons of Jupiter showed is that the Earth is not the only center of motion. So the idea was that the Earth is the natural center, and things fall down because that's the natural place for them to be. What he's doing is overthrowing that physics. This is a physics concept, the idea that the center of the Earth is the natural place for things to be. What he's showing is that that idea is wrong, that there are other centers of motion. The phase of Venus, so here's another picture from his notebook. So when Venus he saw, for one thing, that Venus is round, and it undergoes phases depending on its relative orientation with respect to the sun. And when it's a crescent, it's big, and when it's full, it's small. And that tells us that when it's full, it's far away, and when it's between us and the sun, it's close. And that tells us that Venus is going around the sun. So that's another example of the Earth not being the center of motion. Okay? He discovered, as you saw in the previous slide, craters and mountains on the moon. That means that there are things happening up in the heavens. That was another of the old concepts, was that the heavens are immutable. The moon actually has mountains and other features similar to what's on the Earth, so the heavenly realm is not perfect. He also observed sunspots and noticed that it's spinning. Sunspots are going around when you watch. And also the sun is not a perfect object either. So all of these things put together were basically final proof of the Copernican cosmology. Now I say final proof because it's sometimes people get the misimpression that Galileo actually provided the first evidence. That's not true. There was a lot of other evidence before, not nearly as conclusive as this, but in fact the general consensus among astronomers was already in favor of the Copernican theory even before Galileo did his measurements. But this was really the nail in the coffin for the old cosmology.
It eliminated the Ptolemaic, but not the Tycho Brahe.
I'd have to think about that. Some of these measurements actually are contrary to his cosmology too. But I'd have to think about each of the elements in detail. All right, now one of the things, as I mentioned, and it's going to come, is, all right, we know from these measurements, for example, here, that the Venus is going around the sun, and we know, you can see that when it's on the far side, you can tell the ratios of the distances from the ratios of the sizes. Right? When things are farther away, they're smaller, just the inverse ratio. But we don't know the absolute distance. So the question was in the 17th century, how big is the solar system actually? And that requires some other information. You can't just get it from looking at these objects. And the first measurement was done in 1672 by Cassini and collaborator Richter. So what they did was they looked simultaneously at Mars, one from Paris and one from Cayenne, which is in South America. They are about 7,000 kilometers away, and what you see is that Mars appears to be in a different place on the stellar background. And so you can measure this angle. And just by triangulation, we know this angle, we know this leg, you can tell this distance. Okay? So that's a separate piece of information. The angle's really small. It's only 1% the diameter of the moon. But from that angle, we get that Mars, at least when this measurement was made, was 55 million kilometers from the Earth. The important point being the solar system is really big. This is a lot bigger than anything that people have thought of before. Now, I have to remind you, the Greeks actually had an idea of how big the solar system was. They knew how far the moon was, 240,000 miles. They tried to measure, Aristarchus tried to measure the distance of the sun, but you can't measure, these angles are way too small to measure without a telescope. So this is the kind of science that's enabled by having more accurate measurements. Okay? You basically need to be able to make very precise measurements of very small quantities in order to measure these very large distances. So this is known as parallax. This kind of measurement is useful out to several thousand light years. That's a big distance, but it's still inside our galaxy. So parallax is a useful distance measurement, but not on modern cosmological distance scales. So we'll have to talk about what the new methods are later. Okay, one important physics result of the measurements, also by Cassini and Huygens and Roemer, was the measurement of the speed of light. So this is a place where the astronomical developments led directly to physics measurements. The speed of light. What they did was they noticed that if you look at the orbit of one of Jupiter's satellites, it appeared to come earlier when the Earth is here and later when the Earth is there by about 22 minutes. And the interpretation is that's how long it takes for light to travel this distance. Now that we've figured out the size of the Earth's orbit, we can then use the speed of light, which they got not too accurate. Their problem was actually their clocks weren't accurate enough. It wasn't a problem of the distances. It was a problem. Getting the speed requires time measurements also. And so this connection between astronomy and fundamental physics is actually a continuing relationship. Physics helps astronomy, astronomy helps physics. And it's been going on for the last 400 years. Okay. Now, telescopes nowadays, a lot of them are made with mirrors. You can make a telescope also with a mirror because a curved mirror can focus the light in a very similar way to a lens. Mirrors have some advantages. One is, a mirror can be flat. That is, it can be very thin, and therefore a large mirror will be lighter than a large lens. So it makes it easier to make very big telescopes. I'll show you some of the modern telescopes. There's no way you could even conceive of making the modern telescopes with lenses. The other one is, which I haven't discussed, is that optical glass has the index of refraction of glass depends on wavelength, and therefore you get what's rainbow effect. Rainbow effect is not a good thing when you're doing astronomy. It may be good for other things, but not for astronomy. So that's one, mirrors don't have that. The focal length of the mirror only depends on the shape of the surface. And as I say, yeah, so the mass of a lens goes as the volume, the mass of a mirror goes as the area. And so for big areas, you win with mirrors. But mirrors have a big disadvantage. At least in the olden days, when mirrors were made of metal, they didn't reflect a lot of light, and the surface is corroded. And also, the focus is in the path of the light. So if you want to look at the image, you're blocking the light. That's a solvable problem, but nevertheless, it's a problem you have to deal with. Right. But in fact, these disadvantages outweighed the advantages until the mid-19th century, until basically silvered glass was invented. So that's another technological development that enabled telescopes to work better. So this problem of putting the focus here, basically to solve that problem, you just put another little mirror near what would have been the focus, and it puts the focus off to the side. So here's a telescope invented by Newton. It's called a Newtonian telescope. The light comes in, there's a mirror here, and it gets bounced off, and you actually look, the eyepiece is off to the side. That was Newton's solution. Mr. Cassegrain actually had a better solution. He put the mirror and the focus was down here. The reason why it's good to have the focus here is that puts, see, when the telescope, here, this is a more modern telescope, it's pointed up in this direction. The mirror is here. The focus is, the light comes down through a hole in the mirror, and the camera is here. It puts all of the measurement apparatus at the bottom of the telescope where it's easy to get at. You don't want to have to work on your optics up here. It's just an annoyance, among other things. So in fact, this is the solution used by most modern telescopes. So, of course, one other complication which needs to be solved is, if you've ever looked through a telescope, you notice that the moon moves out of the field of view. That's because the Earth rotates. Here's a time exposure. You can see the stars move around in circles around the North Pole. This is how much they move in 30 minutes. If you're just using your naked eye, that's not a big deal. But if you want to take long exposures, it's a disaster. Okay, so you need to rotate the telescope. So that was, what you do is, you mount the telescope on a big axle, and you have the axle rotating. The axle points towards the North Pole, and it counter-rotates just to cancel the motion of the stars. Okay, so this is one example. This is a telescope in Japan. Here's the famous Palomar 200-inch telescope. It does the same thing. This is the telescope. Here's the mirror. And this whole big apparatus is pointed towards the North Pole, and the telescope rotates around it. So you have a whole big mechanical apparatus whose sole purpose is to keep the telescope pointed in the right direction. Okay? I am way behind schedule here. So let's, basically, the problem is, rotating the telescope, if you want to do it smoothly, you need a machine to do that. What it was in the 18th century, basically, every time the telescope moved a little bit, the astronomer would tell his assistant, move the telescope. And that is very tedious and time-consuming and not very efficient. So what you want is a clock drive, something that basically like a pendulum clock with counterweights and stuff like that, and it ratchets itself, and the telescope automatically just moves across the sky. That was invented in the early 19th century. That improved the observing efficiency. The astronomer could just sit there and look at the objects and not have to interrupt himself. and tell his friend, his assistant, to move the telescope. That allowed big star surveys. He surveyed 120,000 stars. You can imagine how tedious that must have been, looking at each of them one at a time. But anyhow, they doubled 4 times the previous known number. The important science goal is that he is now beginning to map the structure of our galaxy. This is now enough stars that you can begin to see the distribution of stars in the sky and the structure of the galaxy. Okay? It also, as I've mentioned, you need the accurate pointing is important if you want to do long exposure photography. I'm anticipating it because photography wasn't invented till about 20 years later. But this technology was needed if you want to take time-lapse photographs. I'm getting ahead of myself, but I want to mention it because the other way to solve the problem, instead of just pointing at the North Pole and rotating, that's very complicated. You saw that picture of the Palomar telescope. There's a very complicated mechanical setup to get that, to make the telescope point. It's actually very difficult to do for large telescopes. It's simpler just to have 2 axes of rotation. One this way, it's on a turntable, and the other one this way. So one rotates the telescope around like this, and one moves the telescope up and down. Much simpler mechanical setup. The problem is, the speeds of rotation are constantly changing with time. It's a trigonometry problem, which I don't want to get into, and you need computers to solve it. So this solution, even though it's mechanically much preferable, awaited the development of computers before it became the preferred solution. And so nowadays, actually, this is one modern telescope. Here's the turntable, and here's the elevation. That's how all the modern telescopes are made. It's mechanically much simpler, and you rely on computers to calculate the speed at which all the rotations have to happen. This is a practical application of astronomy, which you probably all know. There were a couple very popular books about 5 years ago. If you want to tell your longitude, how far east and west you are, that's not so easy to do. The way you can do it is if you have an accurate star map in the sky and you look directly north, see here's the North Pole, and you ask yourself, if you know what time a particular star crosses that line, you can tell your latitude. But you need to have accurate clocks, and if you want to measure, well, here we are. If you have a clock accurate to a minute, that's about 1/4 degree of longitude, which is about 15 miles, which is not really quite good enough, because if you're near some unknown shoreline, 15 miles could be a disaster. You really want clocks that are good to a few seconds. So those clocks were developed in the late 18th century. And so this is was actually an important astronomical activity in those days. One of the important tasks of the Greenwich Observatory was star surveys of this sort, needed for navigation. So this is the next really huge technological development was the invention of photography in around 1840. So what does it let us do? If you can see fainter objects because you can you can keep your shutter open for as long as you care to. A human eye basically only sees the light, I'm cheating a little bit, but it's basically for about 1/20 of a second. That's why movies that show a frame every 32 frames per second appear to be smooth, because your eye's averaging over that time period. So it doesn't help you. You can't see a fainter object by looking longer. It doesn't help, because your eye doesn't remember what the light that entered 10 seconds ago, whereas a camera does. And so you can look at very faint objects. The other thing is cameras tend to be smaller than people, so this problem of blocking the light path is mostly solved. Also, photography can be used in wavelengths that the human eye can't see, but that's really important. Ultraviolet and infrared photography are an important aspect of modern astronomy. And one can also make very accurate measurements of spectra, which, because measuring it, I'll talk about this a little more. Measuring atomic spectra requires very long exposures. You can't do it, and your eye can't do that anyhow. Even with a prism, now you project the light onto a screen, you can't. It's hard to make accurate measurements unless you can take pictures. Basically, modern cosmology would be impossible if we didn't have this something to let us do very long exposures. Okay, so the first picture of the moon was taken in 1840. It took him 20 minutes because the early films were not very sensitive. This was the first image taken in 1883 that actually shows stars that human eyes couldn't see. So it's not that long ago that telescope technology enabled us to see things that, in fact, were not visible to the human eye. He must have. Yeah, well, the 20 minutes, sure. I mean, the clock drives were 100 years old by now, or pretty much. So this was, yeah, so following the stars with that was a necessary precursor, but, right, but that was already in place when the photography was invented. Right, so this is the first photograph that shows stars that you couldn't see with the naked eye. So because of that, now you can go back and do the same kind of star mapping that you did before and actually see much more detail of the structure of the Milky Way. You can see farther and you can see more stars. You can see farther because you can see fainter objects, which are... Okay? So here, just to give you, just for fun, this is the longest photographic astronomical exposure ever taken. The Hubble Space Telescope in 2003 took a 11-day exposure. And so here, I think this is not the whole image, but it's part of the image. It's called the Hubble Ultra Deep Field. You can Google it and get other images. So this is the picture, and this doesn't do justice of the detail. So this is an expanded view of part of it. These things are all galaxies. There are very few stars in this image. These are almost all galaxies. It is seeing, and I'll talk about that more, the light, because of this really long exposure, you can see really faint objects, which are only a billionth as bright as what the naked eye can see, and therefore they are really far away, about 13 billion light years away, some of them. Yeah?
John, I remember reading that one of these deep field images, and I'm not sure if it was this one, is actually the darkest spot they could find.
Well, that's what they do. Yeah, they don't want to be, they're looking for the distant objects. They don't want to be overwhelmed by the close objects. So they're looking at an empty spot in the sky. And this is the thing that's why there aren't very many stars in it, because we're looking in a direction where there aren't very many Milky Way stars in the foreground. Okay, so all you're seeing are the more distant objects, and they're galaxies. You can't see individual stars at these distances. So anyhow, I just showed this just to give you an idea of where the ultimate, at the moment, of time exposure photography has gotten us. The other really important advantage is spectroscopy. You can measure by passing light through either a prism or a diffraction grating. You can measure the wavelength of light, and you may you have seen that different elements have different spectra. If you pass a light through a prism, you get different colors. So here's Mercury has these two bright yellow lines, and hydrogen has a very prominent red line. And by measuring the distribution of these lines, you can tell the chemical composition of the thing you're looking at. This lets us determine the chemical makeup of these distant objects. This, of course, and so this requires very long time-lapse exposures, so you couldn't do this without a big telescope. And that's even true now. Spectroscopic techniques tend to be limited by the size of the telescope. You really need big telescopes to do really accurate distant spectroscopy. The other thing you can measure, which is important for cosmology, you can measure the speed at which this guy is moving. So if you measure it, suppose you look at hydrogen, the spectrum of hydrogen, and you measure it in the lab, and it's got a very prominent line here near 5,000 angstroms. If you measure it in a star, what you see, stars are mostly hydrogen, what you will see is that the spectrum is shifted. It's just the Doppler shift. So when a car is moving towards you, the pitch is high, and the car is moving away from you, the pitch is low. The same thing happens for light. And so by measuring this shift, you can measure the speed at which the star is moving. In this case, because the light is shifted to red, see, this line is at a longer wavelength, which means redder, so it's moving away from us because it has a lower frequency. And this corresponds to about a speed of about 9% the speed of light. You can measure speeds of objects by measuring the colors that they emit. This is the way speeds are measured in astronomy. Or at least for really distant objects where you can't actually watch it moving. I mean, for planets and stuff, you can actually see them moving. I'm talking about if you're looking at a galaxy which is 1 billion light years away, this is how you measure its speed. Okay. Now, spectroscopy actually led to a couple important physics discoveries. The Herschels discovered at the beginning of the 19th century that there was actually, if you pass the light through a prism, there's actually light out here beyond what you can see, and also light out here beyond what you can see. The infrared beyond the red, and the ultraviolet beyond that. That was a new physics discovery. And the spectra, another physics discovery was that when they looked at the sun, they found some emission lines which hadn't been seen before, and it turned out it was helium, a then unknown chemical element, which is helium. Helium is rare on the Earth, but it's actually about half of the sun. And it wasn't discovered on the Earth for another 30 years. And yeah, it's only a quarter of the sun. All right. Right. But spectral analysis, as I said, requires photography, very long exposures. One of the things you can do is you can look at hydrogen atoms on Earth and measure their properties. You can then say, gee, has the laws of physics changed over the last billions of years? Well, we can tell by looking at hydrogen atoms in distant galaxies and seeing if the orbits of the electrons were the same then as they are now, for example. And so you can test the constancy of physical laws. See, the reason is when you look at distant objects, we're looking back in time because of the finite speed of light. 1 billion light years away means a billion light years away means 1 billion years in the past. So we can tell whether the physical laws are the same now as they were then. And as far as we know, to very good accuracy, there's no observed change. So that's an interesting sidelight. Right. So this leads up to our ability to measure things outside our galaxy. Basically, the simultaneous measurements of speed and distance, the way we measure distance is you need to have stars of a known brightness. I'm not going to talk about that at all. There are certain kinds of stars whose brightness is known, and you can look at the same kind of star in distant galaxies and infer the distance because you know how bright they actually are, and because of the inverse square law. Did I mention that? Not here. By using the inverse square law, the fainter it is, the farther away it is, so you get the distance. Okay. What that meant was, by measuring distances, it turned out many of the things that people just thought were nebulous, sort of blobby things, turned out to be, this is their term in those days, turn of the 20th century, island universes, that is, other galaxies outside the Milky Way. This was actually a very contentious issue until the 1920s, partly because of some very important but incorrect measurements. That's something you always have to worry about is, well, it's life. You're always pushing the edge of what's doable, and mistakes get made. But they usually get corrected. The thing that was observed was how distant galaxies are moving away from us using that Doppler shift. Then the farther away the galaxies are, the faster they're moving. And so here's the Hubble's original data from 1929 measuring the speed as a function of distance. And if you believe that that's a straight line, I'm not sure I would have believed that that's a straight line. But anyhow, that was pretty convincing in those days. This was the first measurement of what's called the Hubble expansion of the universe. If you see everything moving away from you and extrapolate back in time, that tells you that at some time in the past, all the stuff was here. Right? If you see everyone walking away from you and you say, gee, as long as they're walking at the same speed, that means they're all coming from where I am. That led to the concept of the Big Bang, which was a very controversial idea until the 1960s. This was confirmed by other methods with radio telescopes, so I'm not going to talk about it. The modern measurement, though, of the expansion of the universe, this is now, you notice this is speeds up to 1,000 kilometers per second and distances of a few million light years. A few million light years is the distance where you can see there's a couple dozen galaxies within that distance. Nowadays, the measurement is made out to a few billion light years and speeds correspondingly big, and you have a nice straight line. So, in fact, and all of Hubble's data, all of these points lie somewhere down here on this plot. So you need, in order to make this plot, you need very big telescopes so that you can see very far away. You need very long exposures. All of the modern technology is needed in order to make a plot like that, because these galaxies are very faint. Okay, so I think I mentioned this before, right? Distance is time, just because of the finite speed of light, and that's how we measure the evolution of the universe. If you extrapolate backwards, the question is, how long ago was it that those galaxies were all where we are? The answer is 13.7 billion years. So that's how old, as far as we know, that's how old the universe is. When people talk about what happened, ask you what happened before that, the proper answer is we don't know. There are no believable physical theories that explain what happened before that. So that remains to be discovered. Basically, well, anyhow, okay, I'm not going to go into details of how this is known. That's a whole other talk. So the really big development in telescope technology, as I've already alluded to, are computers. So there's several, I'm going to devote several slides to this development. Computers allowed, as I've already mentioned, bigger telescopes because we now can use the simpler mechanical mounts that require computer controls. It's what's called altitude azimuth. Azimuth is this rotation, altitude is that rotation. That's where this word comes from. It's a much simpler mechanical design, but you need computers to do it. It's following the path of a star across the sky is like drawing, this shows my age. Drawing a circle with an Etch-a-Sketch. Do kids still use Etch-a-Sketches? All right. If you've tried to draw a circle with an Etch-a-Sketch, you know how hard that is. But a computer, it's a simple job with a computer using trigonometry. That's what computers are good at. Anyhow, the other thing is better optics, because we can make lenses with the exact shape to fractions of a wavelength of light. So you can basically make, depending on how much you're willing to spend on it, perfect optics. I hope you won't contradict any of the incorrect optics statements I make. He's an optics expert, I'm not. The other important thing with computers, it's related. Digital photography using CCDs is really the same technology as computers, semiconductor technology. CCDs are more sensitive than film and easier to calibrate. And also, you now have digital images, so you have a telescope in some remote place, like on top of a mountain in Chile. you can send that data immediately to be analyzed. And in fact, some of the telescopes in Chile send their data right over here to NCSA, where they do the data analysis. And the analysis is also, because the data is digital, you don't have to scan, you don't have to look at a piece of film and try and figure out how bright the star is. It's all there in digital form already. So the analysis of the images is also done by computer. The other thing is you can now have a huge amount of data. I mean, imagine how tedious it was to examine 120,000 stars by hand. We're talking now, the camera that I'm working on, which I'll talk about, I hope, at the end, will be a 3 gigapixel camera. Each image will be 6 gigabytes. That's about 1,000 times bigger than the images you get on your pocket camera. In 10 years, it'll take 1 million pictures. We're talking about data, huge data sets, 100 petabytes, just to set the scale. That's 100 million gigabytes. So that's a gigabyte is, well, depending on what your computer is, that's a lot of data. Anyhow, but that's what NCSA is good at. And right. So these are all things that are enabled by computer technology, and this means that we can now do analysis of data in detail, to exquisite details that would be completely impossible if you had to do it all by hand. Second thing that computers enable are robotic telescopes. You don't actually need the person to be there to operate the telescope. So there are two examples of that. One is, I'll get to this in a minute. One is you can now put telescopes up in space. This guy's been now orbiting for 20 years, and people have only visited it 2 or 3 times. It's basically a robot, the Hubble Space Telescope, and it does amazing stuff. The other thing is, though, even on the Earth, when something exciting happens, like an explosion that somebody else observes, you very often want to follow it up. So here's an example. Here's a little cluster of telescopes on top of a mountain in Chile. It's called the PROMPT project, led by North Carolina. When people see a gamma ray burst, you want to follow it up with optical telescopes. It has to be done in a few seconds because these explosions are fast. And so this is all done remotely. There are no people inside these telescope domes. It's all done using the internet to send the signals and computer-controlled telescopes. What else? Computers allow us to fix the optics. One of the problems with the telescope looking at the sky is that the atmosphere is in the way, and the atmosphere wiggles due to various things. What happens is the light from a star comes in, it's a nice smooth wave, but the atmosphere has dense regions and undense regions, and by the time the light reaches the ground, the wave is wiggly. This is why stars twinkle. When you see a star twinkle, it's because it's jiggling back and forth. We want to get rid of that. That's not a good thing for astronomy because it smears out the image. If you've got a really fast computer, you can measure the shape of this wave and fix it. You need to be able to take 1,000 measurements a second. You need to have a flexible mirror. So here's a picture of a prototype. So this is a mirror, and these things are all little fingers that push and pull on the mirror, changing the shape of the reflective surface. It's what's called adaptive optics. And you can take a picture that would look like this. This is the stars near the center of the galaxy. There are lots of stars in this picture, and they're all sort of fuzzy and they overlap. It's really hard to see what's going on. If you can do the adaptive optics and get much smaller images, you can now see, gee, there are lots of little stars there that you couldn't see in this picture. So you get much better resolution if you can get rid of the distortion of the image using adaptive optics. This is very, as I say, you need a lot of computing power to do this kind of thing. But there are telescopes that do it. I mean, these are real images. And here's just another example of a thing that looks like a star, but in fact is a double star. Just because of the better resolution. And the last thing, the telescope, some of the telescopes being built now have mirrors that are 30 meters across. That's bigger than this room. There's no way you are going to make a single piece of glass that big. You've got to make, if you want to have a mirror that big, you have to make it out of tiles. Now you have to be able to control, now you basically have a couple thousand independent mirrors. You want to make them into a smooth surface. Well, computers are good at that kind of thing. You look, is the image distorted? Sure, I'll move this mirror a little bit this way and move this mirror a little bit that way. Computers can do that kind of calculation very quickly. There's a telescope under construction. This is a design drawing of a thing called the 30-meter telescope. So, to finish up, this is one of the things that I'm interested in, is the dark energy. Remember I showed you that Hubble plot. The recession speed gets bigger and bigger as you get farther and farther away, but it's not really a straight line. It's a curved line, and the shape of the line depends on the amount, among other things, the amount of dark energy in the universe. So we want to measure the shape of this curve. That requires a lot of data. We need to measure, remember, the time and the speed. We need to make accurate measurements. We need a lot of statistics. Basically, the distance is measured using supernovas. There's a particular kind of supernova whose brightness we know. As I say, remember, distance is difficult to measure. One way to do it is if you have objects whose brightness you know, whose actual brightness you know, then the apparent brightness tells you how far away they are. And so that's what's called a type 1a supernova. And so this is how the dark energy was discovered. This is a graph of what the data will look like with an experiment I'm currently working on. It's showing the deviation as a function of time out to 7 or several billion years of the deviation of the brightness of these supernovas from what you would have if there were no dark energy. We're talking about a 15% effect. It's not tiny, but if you want to make accurate measurements, you want these error bars to be small. That's one of our goals, is to try to characterize the dark energy more accurately than it has been so far, because frankly, we don't really have any idea what the dark energy is. One of the ways to find out is to measure its effect on the expansion of the universe, which is its gravitational effect. So that's one of the measurements. So that's one of the goals of our physics, of our measurements, is to measure the properties of dark energy. We also get at the dark matter also in similar ways. Oh, yes. Let me just show you what you measure with supernovas. This is an amazing movie. I hope it works. Yes, it does. So this is a movie made by the Berkeley supernova people. This is a picture of a galaxy. It has dark bands here because there's dust absorbing the light. That's a typical feature of galaxies. There's going to be supernova here. This is a graph of how bright that supernova is, a function of time. When you see the movie, you'll see this. This is several months. And this is the spectrum, taking spectra of the colors of the supernova. This is real data. And just to give you an idea of what we've got, I've lost my cursor. Where is it? Maybe I can. Oop. Uh-oh. There. The other way. Ah, there we go. I just moved it off to the other screen. Did you see the supernova here? I'll play it again. It's bright. then it fades away. So it's a big explosion. Basically, the star has run out of its fuel, and eventually the gravity is so strong it collapses, and that causes a big explosion. It takes about 2 weeks for it to rise up to its peak intensity, and then it decays away over several months as the fireball expands and fades away. Okay, and so this is the kind of things that we want to measure. We measure how bright it gets to be because it's what's called a standard candle. We know what its actual brightness is, and therefore we can tell how far away it is. We need the spectra because we need to know what the chemical elements are. There are different kinds of supernova that have different chemical makeup, and in order to avoid contamination of our sample, we need to do spectra to get rid of the wrong kind of explosions from our data sample. Now, most of the ones we use for cosmology, this is a very nearby galaxy. This is very unusual. Most supernovas are so far away in very distant galaxies, so you won't see this whole galaxy. All you'll see is a flash of light out in the darkness. But that's the kind of measurement that's made, and you can see it takes a lot of information in order to make these measurements. So telescopes in space, what's the advantage of a telescope in space? The big advantage is that space is almost black because you're not looking at the sky. On the ground, you have the sky. So here are two, this is all drawn by hand by me. A star here, if the star has the same brightness but on a brighter background, it's harder to see. The other thing when you're out in space is you don't have the atmosphere, so the images are fuzzy. On the ground, this thing would be bigger because of the worse resolution. The thing here that I've drawn actually has the same amount of light as the one here, but because it's bigger, it's again harder to see. So as you go to the ground, more background, worse resolution, it becomes much harder to see objects, faint objects. Okay, so that's one thing. There's no gravity. One of the problems with big telescopes is when you rotate the mirror, the gravity is different and the shape of the mirror changes. That's a big problem because the optics is degraded because of the gravity. That doesn't happen with the Hubble telescope because it's in a gravity-free environment. All right, the other thing is the atmosphere absorbs ultraviolet and infrared and also depends on the weather. So out in space, you can see all the wavelengths that you'd like to see, and it doesn't depend on the weather. Okay, so that's the reason why people put telescopes up in space. So what's the future? So one thing of which I've already mentioned is to build bigger telescopes so we can see fainter objects. There's a 30-meter telescope. That's a Caltech project. This is a European project, so they're going to build a 40-meter telescope. Anyhow, as I mentioned, they have to be multi-mirror. You can't make a single piece of glass. But the adaptive optics will give these telescopes incredibly good resolution, but over a tiny field of view, actually smaller than Galileo's field of view. So we're going back to, you need to know where to look if you want to use these things, because you're only looking, it's like looking through a peephole, but you've got a really good resolution. So if you want to look for planets, for example, you have a star and you want to see if it has planets, you know where the star is, you look at it, you have such good resolution you can see the planets. I'll show you. The new space telescopes, you probably read in the paper about the Webb Space Telescope. That's going to get launched in 2018. I don't have that here. It's on the next slide. And the project I work on, so this works out in space, so it's optimized for the infrared because that's one of the things that's hard to do on the ground because of atmospheric absorption. So their goal is, because of the redshift, because of the Doppler shift, when you look in the infrared, you can see things that are farther away, because the farther away things are, the faster they're moving, the redder they are. And so if we want to see the first stars that were ever made, we need to be able to look out in the infrared. That's one of the primary goals of the Webb telescope. The telescope I work on is not a huge telescope. Its main thing is it's got a huge field of view. I'll show you that one too. Its purpose is to do big surveys because it's got a big field of view to look for new things. If you want to look for new things, you have to be looking over a big search area. And as well as I mentioned, measuring the properties of dark matter and dark energy. Let me just give you a little more detail. So here's a picture of the 30-meter telescope as it's designed. The construction of this is just about to begin in Hawaii. So because it has such good resolution, let me give you an idea what that means. Its resolution will be, well, I don't think this means anything, a milli-arcsecond. That angle corresponds to a 1 centimeter resolution if you're looking at Los Angeles from New York. But to put it in astronomical context, it means if you're looking at a nearby star, your resolution is 100,000 kilometers. That's about the size of a big planet. So we can actually begin to image planets, not just see them, but actually, for the bigger planets, make some measurement of what they look like. This is only just beginning, but you have to start somewhere. I mean, that's amazing resolution. That's good enough to image large planets, what are called super Jupiters, and to study planetary atmospheres. That's what we need to do if we want to look for life. So that's an interesting question, is suppose you were an astronomer on Jupiter and you want to know if there was life on Earth. How would you do that without actually going there? One of the things that's a smoking gun for life on Earth is free oxygen, which is produced by photosynthesis. If you don't have plant life on Earth, then all the oxygen gets tied up in minerals. Things oxidize. So if you have free oxygen in the atmosphere, that means there's life on the planet. That's the kind of signals, spectroscopy that you would want to do to look at the planetary atmospheres to see if there are living organisms, things that have the same chemical processes as us. So this is feasible, maybe, in the next 10 to 20 years when this telescope is built, and also its European counterpart. So here's these are actual images. Here's a star, here's a planet, here's another star. It's been blanked out. You can see the blanking circle. Here are 3 planets orbiting that star. These are images of planets. Now these are all super Jupiters, and they're also far away from the star, more or less plutonium distances. So this isn't what we want, because in order for a planet to support life, it's got to be a lot closer to the star, and it's also got to be a lot smaller than a Jupiter. But this is the beginning of looking at planets around other stars. Let me not get to that. So here's the Webb Space Telescope. It's got a big mirror, but it's also multi-mirror. The reason why it's multi-mirror is you can't put big mirrors on rockets. You're limited by the size of the rocket, so you have to launch it in lots of little pieces and have it assemble itself. It's a robot. It's got to put itself together. That's why it's complicated and costs a lot of money. Anyhow, what it's going to do is it's going to look for the first stars and galaxies, and maybe also, because it's in the infrared, it can also make some measurements that are useful for searching for life. And so the last one, which is the project I'm on, is just to give you an idea of what the big mirror is. It's got an 8.4 meter mirror. That's 8.4 meters. There's a person. There are 4 people. This telescope is under construction. This is what it will look like. There's a person. For those of you who are into photography, you can think of this thing as an f1.2 camera. There we are. I don't know how many of you know enough about cameras. That's a fast camera. Right. So what is it going to do? It's going to do basically all kinds of stuff. It's basically a survey. It's going to look for killer asteroids. It's going to look for things that go bump in the night, transient phenomena. It's going to measure cosmology, and it's, as I mentioned, going to produce this giant data set. And it'll start taking data in about 5 years. And I think that's the end. So,
wow.
a little over.
Yeah, no, that was spectacular. It's an exciting time.
It's an exciting time.
Yeah, we're going to know things in the next 10 years that we've been dreaming about for a century.
Oh, it's a good, to my mind, I mean, I'm not working on it, but the search for life, I mean, that's possibly the biggest discovery ever. If we can,
Yeah. So where is your telescope going to be?
Chile, in one of the photographs of the telescopes in Chile is right next to the mountain where this telescope will be.
Fantastic. So I think we have some demo telescopes out there, and I think it'll be a lot of fun for the kids and people who are kids at heart to go have a look through them. I'll take 1 or 2 really quick questions if someone feels like, yes, I really want to ask a question. Any quick questions? All right. Yes, right back here. Why Chile?
Oh, there are 2 places that have the best. It's because the atmosphere is very stable. Remember, the atmosphere wheels things around. The top of the Hawaiian mountains are above the weather, and Chile is fairly dry atmosphere. Water is not good either for astronomy. Those are actually the 2 best places in the world for telescopes.
This has nothing to do with Malbach. No, okay.
That's the wrong country.
Right back here.
Will you be able to get any information about dark matter?
Yes, dark matter. I didn't talk about it, but dark energy and dark matter from an observational point of view are very close. We can't measure one without the other. We'll get them both at the same time.
In the very back.
The Webb telescope is supposed to be launched when?
2018.
When will Webb be launched? Just so we know.
The Webb telescope is supposed to be launched in 2 years.
And John, I've seen roadmaps that have 100-meter optical telescopes in 30, 40 years.
Let's build the 30-meter one.
Let's build the 30-meter one first. All right, fantastic.
I mean, a telescope the size of a football. You're talking about a telescope the size of a football field.
A much more edifying use of a football field. Yes, yes. All right. Well, I first of all would like to thank all of you for coming. I'd like to promise you that if you all keep coming in these numbers, we'll have more food in the morning. It's a great problem to have that we ran out of food, and I'm glad to have you all here. Oh, goodness. Now, okay, I was going to say now might be a good time to go outside and look at telescopes. But thank you all for coming. Don't forget the summer camp brochures, and please come look at the demo telescopes. Thank you again.
Do you have any idea how accurate